Hey y'all, it's Miss Summers with your notes today on igneous and metamorphic rocks. The goal of today is we want to be able to use the characteristics of igneous and metamorphic rocks to determine where they're formed and how they're formed. Okay, so remember yesterday we started by talking about rock cycle, how we have rocks that are basically just combinations of minerals. Minerals are those inorganic, solid, naturally occurring substances. All right. Remember, a mineral can be grouped based on what it's made out of. So, like for instance, all the silicate minerals all have silicone and oxygen in them. All the carbonate minerals have carbonate in them, so on and so forth. All right, today we're going to look specifically at igneous and metamorphic rocks. Remember, the rocks are based on how they're made, not what they're made out of. All right, so we're going to look at both of these and look at them in a little more detail because there are different types of each of these rocks. Okay, so I'm going to go ahead and present. Here we go. Fantastic. So how can we tell where rocks are formed, under what conditions they're formed under, just by looking at them? All right, so let's start with igneous rocks, just a refresher from yesterday. Igneous forms when magma or lava cools and hardens or solidifies. The difference between magma and lava is just where it is, and that's going to be important. Magma is inside of the earth, and lava is on the surface or outside of the earth. Okay? Whether the rock is formed inside the earth or outside the earth changes the texture of the rock. Okay? So when we say texture, when we're talking about rocks, we're going to be looking at what it looks like. Okay? Texture in igneous rocks is based on the size of the crystal grains. So what is a crystal in an igneous rocks? Well, if we look at granite has these really big specks, these really big spots. That's what a crystal is, all right? Crystal size in an igneous rock is determined by cooling time. So remember, lava or magma is either going to cool very fast or very slow depending on where it is. So let's take a look at this relationship. So we have this graph here. It's a nice little line graph. Cooling time is our independent variable. Cooling time affects the size of the crystals, the dependent variable. So basically what happens, if you have a rock with large crystals, that means that it took a long time to cool down, a long cooling time, slow cooling. If there are very small crystals or no crystals, that shows a short cooling time. It cooled very quickly or very rapidly. All right, so what are these different igneous rocks called? Well, our first kind is extrusive. So an extrusive igneous rocks form on the surface from lava. My favorite example of this, of course, is obsidian, my favorite rock. If we look at obsidian, I can tell that it cooled on the surface because there's no crystals. There's no spots here. It's all one shiny surface. All right, X means out, like an exoskeleton or an exit. Okay, that's going to tell you that it's left under the earth, it's now on the surface. It cools down really fast because it's exposed to air. All right. Rocks that are extrusive are going to have a glassy or fine texture. All right. So obsidian is glassy. You can see it's very smooth. There's no spots in it. There's no little speckles. That's what glassy means. Fine. Okay, if I think of something like a fine-tooth comb, all right, fine means small. Basalt, this is what's on the bottom of the ocean. This is like at a mid-ocean ridge. Remember, at a mid-ocean ridge, magma comes up to the surface and cools down really quickly to make that ridge. There's very small crystals. I can't see the crystals unless I had like a magnifying glass. All right, so extrusive igneous rocks form on the surface. Because they form on the surface, they cool down quickly. Because they cool down quickly, they have small or no crystals. And because they have small or no crystals, they have a fine or glassy texture. Okay? The other type of igneous rock is intrusive. So in means inside. These are rocks that form inside the earth. An example would be granite. Granite is a fine example of an intrusive igneous rock. This is what most of the Earth's crust, the continental crust at least, is mostly granite. Because it forms inside the Earth, this magma is going to cool down very slowly. It's almost like being in a thermos, okay? Imagine this magma is soup, okay? If I were to take this soup and pour it out into a bowl and expose it to the air, it would cool down really fast. But if the soup stays in the container, okay, in my little thermos that I have, it's going to stay warm longer. It's going to take a long time to cool down, okay, because it's insulated. So this is cool. This is going to cool down over thousands and millions of years. That means you're going to have very coarse textures. That means the crystals are very big. This is diorite, I think, or dolomite. I think it's diorite. I don't know. IDK. It's irrelevant. Okay. But there's very big crystals. There's big spots. Okay. That's a coarse texture. All right. So intrusive rocks form inside the earth. Because they're inside the earth, they take a long time to cool down. Because they have a long cooling down time, they have big crystals. The big crystals make the coarse or very coarse texture. All right. And then we have some igneous rocks that are weird, that have both large and small crystals. All right. So these are called porphyritic. So they have large and small crystals. All this means is that there were two separate cooling events. All right, whoops. So we have this porphyritic rock. I see my big crystals kind of sprinkled throughout, but then I have these large areas where they have small crystals. So what happened here most likely is these crystals were cooling down inside the earth. That was the intrusive part. And then this volcano erupted, okay? And then the rest of it cooled very quickly. So you had a little long cooling time and some short cooling time. Porphyritic. All right, so a very quick practice question. Lava, where is lava? Lava is on the Earth's surface. How does cooling rate affect the size of the grains? The longer the cooling rate, the bigger the grains or the bigger the crystals. Short cooling time, small crystals. Crystals form in molten rock as it cools down. Okay? All right, our next type of rock is metamorphic. Metamorphic, okay? So we have this little cartoon here that it doesn't represent metamorphic rock, but it represents metamorphism, okay? So we see all these bugs looking at this cocoon that a caterpillar made, and what is going to come out is not going to be a caterpillar anymore. It's going to be a beautiful butterfly, okay? That's kind of like metamorphic rocks because they change form, okay? So a caterpillar metamorphosizes into a pretty butterfly. Metamorphic rocks start off as one type of rock and then are changed to another. So this example, granite metamorphosizes. Granite becomes gneiss. This is called gneiss, everybody. It's still the same stuff. It's the same chemical composition. It's just different physical properties and different structures. That's why it looks different. All right. Metamorphic rocks form from intense heat and pressure. So if you watched the videos yesterday, we watched a video on like the Manhattan skyline. The Manhattan skyline is made out of metamorphic rocks. Those rocks formed under intense heat, upwards of like 500 degrees. That heat comes from magma, and pressure comes from plate tectonics. Okay, so again, with the Manhattan skyline, that rock, as those islands pushed towards what's now North America, it buried those rocks inside the earth and squished them. Okay, so because you need heat and pressure, most metamorphic rocks are going to form deep below the Earth's surface, okay? You're going to have to really dig far down to get to them. Metamorphic rocks are classified by their structure, okay? It's basically what they look like. So we have 4 examples here. I think this is also nice. Yeah, I think these are both nice. And then we have marble and quartzite. Now look at these two compared to these two. What's different? And hopefully you're like, oh, these two have stripes and these two don't. That's exactly right, okay? That's what you're going to look at for a metamorphic rock. All right. Metamorphic rock can be foliated or non-foliated. So a foliated rock happens when you have pressure flattening the crystals and pushing them into parallel bands, okay? So bands are like stripes. Foliation, you're going to have very high pressure, and it has to be from one direction. Okay, so let me see if I can't find a picture here. Okay, here we go. So I'm going to minimize this just a quick second and then bring myself up to the foreground. Hi, everybody. Okay, so directed pressure. Okay, here's my rock that I'm about to turn into a metamorphic rock right here. Okay, I've buried it. I'm exposing it to a lot of heat. Okay, maybe it's near like a plate boundary or something like that. Directed pressure means the pressure is coming from primarily one way. Okay, the foliations, the stripes, are going to be perpendicular to that direction. Okay, so that's how you would end up with something like this. Okay, going back here, percent. Awesome. Some examples of this would be slate, schist, and gneiss. All right, so there's our pretty stripes and gneiss. This is, I think this is schist, I think being the operative word. But you can see the banding patterns. All right, in a non-foliated rock, there are no visible parallel bands. So example, we quartzite, which we have a picture of, and marble. This forms under relatively low pressure, low pressure or uniform pressure. Uniform means that the pressure is coming from all directions, okay? So you don't get those stripes. Here we have some marble, and some people might say, well, I have marble at my house, or I've seen marble at like Home Depot or whatever, and it did have stripes. So doesn't that mean it's foliated? It's not foliated because these stripes are not parallel. Okay, remember, parallel means that they aren't going to cross each other. These little marks do cross, so that's why it's not foliated. All right. The last thing I want you to know for metamorphic rocks, so they can be foliated or non-foliated, is the parent rock, what a parent rock is. So a parent rock is the rock that a metamorphic rock was before it became metamorphic. Okay? Can any type of rock become metamorphic? So if we look at this example, so we have limestone, and then it says sed, and shale, which says sed, and then granite, which says igna, and slate, met. These are the types of rocks. So limestone and shale are both sedimentary. Limestone, when exposed to heat and pressure, becomes marble. Shale, when exposed to heat and pressure, becomes slate. Okay, so sedimentary rocks can become metamorphic. Can igneous rocks become metamorphic? The answer is yes, because we have granite and quartz. Both of those are igneous. Granite becomes gneiss. Quartz becomes quartzite. Okay, that's cool. What about metamorphic rocks? Can I take a rock that is metamorphic already and make it into another kind of metamorphic rock? And the answer is 100%, of course. Slate, remember, slate is shale that's metamorphosized. Slate, if I add more heat and pressure, becomes schist. Okay? Talc, all right, which is metamorphic, becomes soapstone. Gneiss, that should say igneous, all right, can also become a type of schist. All right, so any rock can become metamorphic. Any rock can become, actually, I don't know why I said gneiss is already metamorphic. I'm sorry, guys. Gneiss can become schist as well. Okay, that's my bad. Gneiss is metamorphic. I'm silly. All right, any type of rock can become metamorphic as long as it's exposed to heat and pressure. Okay? So those are your notes today. Let that marinate on your brain, and then go ahead and do your check for the day.